The answer may not surprise you. Most would undoubtedly speak about NASA's past and present space flights and recent developments of new technologies and breakthroughs in science. While NASA does focus much of its efforts on projects that are outside of our home planet, much of NASA's research and development is performed closer to home. The first A in NASA stands for aeronautics, and that focus on aeronautics is just as strong today as it was in the past. Looking back to the early history of NASA and its predecessor agency, the NACA, much of the pioneering work in aeronautics was carried out by experimental aircraft that later became known as X-planes. X-planes are a series of United States aircraft and rockets used to test and evaluate new technologies and aerodynamic concepts. The X designator denotes the unique experimental research mission. For decades, these unique aircraft flew around California's high desert, pushing the envelope of flight mechanics and providing a solid foundation for our understanding of aeronautic principles to help solve major aviation challenges. X-planes and other prototype air vehicles hold a special place. They're a glimpse into the future of what supersonic aircraft and spacecraft may become. Over the last 7 decades, they've been a proving ground for developments, including delta wings, tailless aircraft, and supersonic flight. Vehicles that fly at supersonic speeds are flying faster than the speed of sound. The speed of sound is about 760 miles per hour at sea level. These speeds are referred to by Mach numbers. The Mach number is the ratio of the speed of the aircraft to the speed of sound at altitude. Flight that is faster than Mach 1 is supersonic. Supersonic includes speeds up to 5 times faster than the speed of sound, or Mach 5. From the first flight of the X-1 in 1947 all the way through X-plane flights in the early 80s, NASA and the military have built many X-planes that help challenge and change our understanding of aeronautics. Eventually, the emergence of advanced computing coupled with constrained budgets helped slow the development of full-scale X-planes and led more to the use of smaller, uncrewed aircraft for testing. But even with computer simulations and small unmanned aircraft proving to be powerful tools in the development of new aircraft, researchers understand that there is still a need for the development of full-scale, piloted X-planes to help close gaps in our understanding of aeronautic principles. The Lockheed Martin Skunk Works team, contracted by NASA, has built a new full-scale X-plane called the X-59. This new mission, called QueSST, has 2 goals. First, design and build a unique shape that will reduce the loudness of a sonic boom reaching the ground to that of the sound of a closing car door. And second, once built and tested, fly over a number of U.S. communities to gather data on human responses to the sound generated during supersonic flight to make sure the noise is acceptable. NASA plans to hand over this valuable data from communities to federal and international regulators to help change the rules. If successful, this could lead to a new generation of commercial supersonic aircraft operating over land, clearing the way for time-saving, faster flights for the flying public. We will speak with researchers on the cutting edge of this technology to explain how this type of aircraft will be built and utilized, and how this aircraft has the potential to be the pathfinder for supersonic commercial aircraft of the future. And we will follow the X-59 team as they move from the testing and validation phase all the way up to the first test flight of this new X-plane. That sound is well known to military personnel and citizens who live close to certain military bases. But supersonic aircraft have been around for many years. In 1947, Chuck Yeager became the first person to fly faster than the speed of sound, around 760 miles per hour. Since that time, many military aircraft routinely fly past the speed of sound.
But soon after sonic booms became a regular thing, the military advanced very quickly to having supersonic capable aircraft. And then really very soon after that, we began to see the ideas for supersonic airliners. So it was really very exciting, and it really had a lot of possibility. But the military, where sonic boom first was kind of a novelty, it pretty rapidly became apparent that on a large-scale basis, the noise was just not going to be acceptable.
A sonic boom is heard after an aircraft breaks the sound barrier. And in fact, it can also be heard on the ground all along the path the airplane travels.
Well, basically, when you go above the speed of sound in an aircraft over land and even over water, you generate a sonic boom. So essentially what's happening is that the air just can't get out of the way fast enough of the airplane because it's going so fast. And so it generates a shock wave. And the shock wave propagates down to the ground, and it sounds like almost like an explosion or a loud boom, and it can startle people, it can rattle windows and cause problems. So for this reason, commercial supersonic flight is basically banned over land. Even military flights are restricted to certain areas because the shock waves can cause so much disturbance on the ground.
Up until about 20 years ago, there was one commercial aircraft that did not fly over land, but did operate at twice the speed of sound over the ocean between Europe and America. This supersonic jet was called the Concorde, and first arrived on the scene in 1969. The Concorde was so fast that a passenger could take off from Europe at sunset and outrace the sun in time to land in the United States to see the sunset again. Initially, it was believed that the Concorde could be used for overland flights as well, but that thought quickly changed with the realization that all the communities within the Concorde's flight path would be subjected to a sonic boom. So in 1973, the Federal Aviation Administration issued an order banning supersonic flight over land, leaving the Concorde to only fly over the ocean. Finally, in 2003, high expenses and limited flight routes forced British Airways to retire the aircraft for good. Fortunately, the decades of flights by the Concorde didn't go unnoticed.
And so with the Concorde, we learned a little bit more about sonic boom, and then we also learned a little bit more about some of the environmental challenges and the airport noise challenges that went along with that, and economic challenges and so on. The last flight of the Concorde, we really realized that we'd have to have a lower boom type configuration that would be more feasible for a commercial airplane. Today, I think we have the advantage of many things. A lot of our tools and technologies that we develop along the way, some of those computational tools, for example, are much stronger, and our computing speeds are much faster, where we can sort out these sonic boom challenges. We've also learned a lot more about sonic boom shaping of the airplane.
So it's really interesting to see the evolution in recent years, in the last decade or so, in our thinking about how to design a supersonic airline. I mean, the math has been around since the 70s. And as a matter of fact, Christine Darden, one of the hidden figures that didn't get into the movie, was really one of the mathematicians that helped define that theory.
The Russians, the English, and the French, and the United States were all going to build a supersonic transport. In '71, the United States had done some flight tests over Chicago and Oklahoma City, and they got so many complaints about the boom and calls and cracked windows and so forth. The United States canceled their SST program. My boss walks into the room as my first assignment. He hands me a technical paper from a couple of professors at Cornell University on their thoughts of some ways to reduce the sonic boom. NASA created it because people still wanted to go fast. He says, here, I want you to solve the equations in here, write a computer program for this, and if you've got any questions, I'm next door, come and ask me. Otherwise, go to it.
Dr. Darden and other NASA researchers continued to work on the issue of reducing the sonic boom over the years. But recently, a renewed interest in this field has led to a resurgence in testing.
The problem was we couldn't make a practical airplane that had the sound characteristics that we wanted. the big change that I've noticed in all these years is we went from trying to design the airplane to produce a specific sound on the ground to a process where we let the sound that we want and the airplane design evolve simultaneously. That's really enabled us to design an airplane that not only is quiet, but it also meets all the other performance requirements of a good airplane. It can take off and land, it's efficient at cruise, it performs well. So within a few years, we went from, this is really hard, to, hey, we could really do this. So that was very exciting in that time period.
That exciting work has led to the X-59 design. This aircraft is being purpose-built to literally shape the noise to reduce the loud boom to the sound of a quieter thump. With its unique design, including a long pointed nose and sharply swept wings, engineers and researchers believe they have a chance at beating the boom at its own game. Specific design choices would ensure the pressure waves created by the plane weaken and do not merge, preventing a traditional sonic boom.
So the X-59 is essentially like a supersonic object that might travel through the air faster than the speed of sound. So for example, a bullet could be fired. When you hear that kaboom, you're essentially hearing the sonic boom from that bullet. And there's a trailing edge and a forward edge that kind of creates that pressure wave and that sonic boom. So if you take that and apply it to an airplane, airplanes that have been designed today create what's called an N wave, or a pressure wave that is shaped like an N. So it has a sharp crack at the beginning and the end of that pressure wave. When you want a low boom airplane, you're really lowering the amplitude and you're also lowering the ramp time to that pressure wave. So it's more like a sine wave that allows you to hear a softer kind of thump feature on the ground.
So for a supersonic aircraft to be quiet, in other words, not produce a sonic boom, if you're going to do that design, you really have to take that into consideration from the very start of the design. So the airplane doesn't look radically different from other supersonic aircraft, but there are certain features that are really important.
So the X-59 is a unique kind of one-of-a-kind purpose-built airplane. So when you build an X airplane, is what they call it, there's really several things you're trying to achieve. One is technical. What are the technical objectives that you're after? So a low boom airplane would tend to have a long nose, swept wings, might have a T-tail for stability, a canard for pitch control, and so on. So there's some technical needs to get our low boom aircraft. But then we also, because it's a one-of-a-kind airplane, have a lot of cost needs. So we might utilize, for example, the T-38 canopy, the F-16 landing gear, GE 414 engine that goes in an F-18 in today's fleet. So it's really kind of a combination of cost features and also technical features. And then we've got some facilitating technologies like the external vision system that allow us to do the mission. So it's really kind of a hybrid of things that we have to consider in building a next airplane.
To build those features into an aircraft, NASA turned to Lockheed Martin in Palmdale, California, which is located near testing facilities at NASA Armstrong and Edwards Air Force Base.
NASA has the vision. NASA has the budget. They also have the sort of the charter, if you will, to go and do these things. So they came to Lockheed because we had the know-how in terms of some of our software tools to be able to do that boom prediction, to very rapidly iterate on what the design should look like. And so they use the talents and the knowledge base of industry. We have the industrial base to be able to build an airplane like this, the hangar and all the tools, and then the relationship with suppliers to do that. So it is kind of a marriage, if you will, between NASA and contractors. Obviously, we want to demonstrate this low boom as cost effectively as we can and as quickly as we can, but making an airplane that's very large is very, very expensive. We're using off-the-shelf parts to make this airplane possible. That limits us in what we're able to do. For instance, the engine is an F414 engine out of an F18. That gets us to Mach 1.4. We'd like to go to Mach 1.6 to 1.8, but again, we're using what we can in order to make it affordable to prove out the low boom, to have the regulation changes. We made it as small as we could, as cheaply as we could, but also it's not a stunt and it's the right size to show that you can take these technologies to an airliner.
Although NASA and Lockheed used some off-the-shelf technology, they also completely reimagined the shape of the X-59 to help assure that the sonic boom would be reduced to a thump.
I'd say the thing that's different about this airplane is how focused and purposeful it is. Every single feature on the exterior of the airplane is intentionally designed that way to meet the mission of being a low boom demonstrator. So the entire outer mold line of the airplane, with the exception of the canopy, is completely new. And we had to go through thousands of iterations using computer simulations to really refine the shape. And the devil's in the details when it comes to low boom design. So we had to carefully iterate on everything, whether it's the shape of the canard you see behind me, the nose, the way that we integrated the engine, etc. All those features had to kind of work together so that we stopped those individual shock waves from the aircraft. We stopped them from coalescing and resulting in a loud double bang. And that's the most unique thing, is how purposeful and intentional we had to be with the entire shaping of the aircraft.
Although the aircraft has not flown yet, that hasn't stopped pilots from getting flight time in this aircraft. In addition to the test pilots at Lockheed, NASA built this one-of-a-kind simulator to help prepare the pilots for what to expect once the aircraft takes flight.
The simulator is built from the same blueprints that the aircraft is being built. So this was our first opportunity, even before the airplane's ready, to get in and start looking at how it's laid out. We've already found a few minor things, gauges that we couldn't quite see or things we wanted in different places that before it was actually built, we were able to find these things in the simulator and give that feedback to the engineers. There's a lot of switches on the throttle and the stick that allow us to actuate different modes and displays. And so we get to experiment with all that here in the simulator and see that it works the way we would expect. Beyond that, we get a feel for how the airplane's going to handle. The control laws in this simulator are exactly the ones that the engineers are designing at Lockheed. We expect that the airplane should handle very much like the simulator. There will be minor differences, and that's what flight test is all about, but for the most part, we really believe that what we're doing from a handling qualities or a performance standpoint in the simulator should match the real airplane. It's a build-up approach. Initially, the engineers will power the airplane on and start to make sure that the components and subsystems are all working together. At some point, it'll be a big moment when they power up the engine for the first time and everything's working on aircraft power. Probably have the test pilot sitting in there. Eventually, we build up to taxiing around the airfield. From there, you build up to a low-speed taxi down the runway, then a high-speed taxi down the runway, and eventually we get to what's always called first flight, where the airplane gets into the air. The first flight is a very basic flight. We'll just get airborne, fly it around, make sure things seem to be working, and the real goal of the first flight is just to safely get back on the ground. And then there'll be a lot of looking at data to make sure everything worked the way it was supposed to, and then in baby steps we'll pick up the pace and then we'll start expanding the envelope from there.
As part of this testing, NASA will not just be looking at the aircraft itself, but will be validating the low boom noise from the ground and from the air.
We'll be testing at Edwards Air Force Base. We'll have a 15 to 30 mile array of recording equipment on the ground that will capture, as we do a pass with the aircraft, will capture the acoustic levels on the ground that you would hear. A sonic boom stretches for a very long distance. What we call the carpet underneath could be something between 20 and up to 100 miles, depending on the atmosphere that day. We also have a glider that will be flying at about 10,000 feet that will be doing some additional measurements in the air with a shock sensing probe. There's a lot of turbulence on the Earth. You know, you have a lot of variability, winds, everywhere. And that's a really challenging part of the atmosphere for us to model. We've done tests in the past to try to develop turbulence models, but that's going to be a big part of a validation phase, is really trying to understand that atmospheric boundary layer, which really can have a very large impact on what you're hearing on the ground. Just like we have in wind tunnels, we do something called Schlieren imagery. We've perfected a technique to actually do airborne Schlieren measurements, which basically creates a really nice picture and actually lets us see the shock waves coming off of the aircraft. So if our predictions are not matching, the data we're measuring, we can use this imagery to try to understand where some of that discrepancy is coming from. So that's a great diagnostic tool for us, plus we get some great images.
Shortly after that phase of testing is complete, NASA will move on to the community overflight phase to get the public's input as to what sound level is acceptable for quiet supersonic flight.
So the main goals of the community overflight tests is to get that public response to the varying levels of the sonic thump. First of all, is it noticeable at different levels, or how noticeable is it? How annoying is it? And as we develop that relationship of the sound level to the annoyance level, we can then take that information, try to create as much of a nationally representative data set, and then provide that to the regulators that they can then use to come up with a noise limit or a noise standard to permit overland supersonic flight.
That validation will be an important factor to determine if the public agrees the noise from these new vehicles is acceptable. As we move closer to the goal of having the X-59 fly for the first time, the excitement displayed by the team is beginning to build to a new level.
The thing that excites me about this program in particular is it allows us to get aviation back on track to where it was in the first 7 decades of flying. Basically, from the time of the Wright brothers until the 1970s, airplanes got faster every single year, kind of like we expect today from smartphones or computers. If you think now back to what iPhones were like 10 years ago, it's remarkable how much better they've gotten. And aviation used to be exactly that same way, until we ran into this sonic boom problem and hit us a barrier. And the barrier was really regulatory. For good reason, a ban was put in place in 1973 on supersonic overland flight because it was just too loud. And no one, including myself, would accept hearing sonic booms on a day-to-day basis. And so this program, I believe, will allow us to get back on track and keep progressing, keep pushing faster and faster like we had been up until the 1970s. And that's really exciting.
I think one of the things that, obviously we look forward to the first flight. That's always a big deal. But I almost compare this airplane to, if you're a Star Trek fan, when the first warp spaceship was done. That's kind of a big deal in the Star Trek world. This is sort of analogous to that. And the airplane will fly, but at some point it's going to go supersonic and it's going to create a quiet boom. And to me, actually, that will probably be more of an emotional moment than the first flight, because that's exactly what this airplane was designed for. And when it flies over and we don't hear it, it's a success.